Alrighty, so let's get into this topic, MPLS fundamentals. So as I said, over the next 2 terms, we're going to be covering this subject of MPLS and or MPLS and VPNs. So as I had mentioned, this is probably going to be one of the most, or the most advanced topic that we do in the course, simply because this is a service provider technology. So out of all the things that we've done throughout the course, pretty much everything has been applicable to enterprises. Maybe with the exception of BGP, but even then, some of the larger enterprises would still use BGP. But the MPLS protocol is never used within an enterprise. This is something which is used only within an internet service provider or a telecommunications company, which of course, internet service provider is a telecommunications company. So we'll just get into this and talk a little bit about what it does and how it works and so on. So we're going to just start off by defining some common terms, describe the way a router forwards MPLS packets. We'll look at MPLS packet flow and packet processing from ingress to egress router. So just bear in mind, we're talking about the concept here of a telecommunications company, and sort of as we're mentioning, a lot of the traffic that flows through their network is traffic that is transiting their network. So it will be coming maybe from a downstream. If you're a tier 2 provider, the traffic will be coming in from a downstream tier 3 and going up to your upstream tier 1 or vice versa. Downloading, from your upstream tier 1 and transiting out to your downstream tier 3. So the traffic is actually servicing the customers of your downstream telecommunications company. And of course, you are selling bandwidth to your downstream and buying bandwidth from your upstream, and sort of so that's kind of the business model in that regard. So when we're talking about packet flow processing from ingress to egress, what we're meaning there is traffic that is transiting through the provider's network. So it's not traffic that is destined for the provider's network. It's not traffic that is destined to any device within the network. It's going through the network. Now, it could also be traffic that is coming in from a customer of that provider and going out to a customer. So, for example, in the situation of a VPN, where you may be providing a VPN service to your customer. So it may be coming in from one customer's site and exiting out to another site of that same customer. So you're actually providing the connectivity between the various customer sites. So in any case, the main point is that when we're talking about MPLS, we are really talking about traffic that is transiting through the service provider's network. Okay, so it's coming in on one router and it's going out on another router. As I said, either from their upstream to their downstream telcos, or maybe from a customer site to another customer's, or to another site of that same customer. So, so we'll look at that flow of traffic. We'll look at configuring up a router and interfaces to perform MPLS forwarding, and look at this thing called label information base. So here we go. Let's first of all examine a regular non-MPLS, just a regular IGP, interior gateway protocol. I mean, let's just say OSPF would be an example of that, and probably a very commonly used protocol within a telecommunications company. So let's just take a look at, before we get into MPLS, let's just take a look at how traffic is processed by an IGP. So it is routed based on the IGP's best path selection. So traffic that is destined for networks attached to router R6 and R7 uses the same path. So here we are, we've got R6 on top there and R7 down below it, and we've got traffic that's coming in on R1. So we're talking about traffic that is transiting through the network. Okay, so let's just say we had some traffic which was coming in on R1, going out on R6, but other traffic that was coming in on R1, but its destination network was actually had to be routed out through R7. Well, what would happen is, based on the IGP, traffic would come in on R1, and the IGP would select the same best path to R6 as R7. It would go up from R2 up to R3, down to R5, and then either out to R6 or out through R7, depending on what the egress router was. But the main point we're making here is that it would always go through R3, regardless of whether the egress router was R6 or whether the egress router was R7. Why is that? Because the best path selection between R2 and R5 is always going to be between R3. Why is that? Because that's what the IGP has decided. The metrics that are built into the IGP have made a path selection that the best path is via R3. Okay, so in a telecommunications network, if predominantly, say that the traffic came in on R1 and went out either R6 or R7, if that was like where most of your traffic went, you'd end up with R3 potentially being very, very busy, that particular path, or let's say the interface between R2 and R3, those interfaces, and then R2 to R5, those interfaces will potentially be maxed out on their bandwidth and potentially become a bottleneck, whereas the other path down through R4 will be hardly used at all. Okay, so what the issue is that you end up with potentially parts of the service provider network being highly utilized and other parts being underutilized. And if you're in the business of selling bandwidth, which they are, right, then you want to be able to sell all the possible bandwidth that you have. And you certainly don't want parts of your network kind of being relatively underutilized. So redirecting traffic from R1 destined to R7 to traverse R4 causes traffic destined to R6 to also use R4. So if you go and tweak your IGPs, metrics in other words, go changing the metrics to say, actually, no, I want you to favor the other path, well then you have the other problem, okay, in that it all now goes through R4. Okay, so what we're saying is that the IGP is a fairly you can't fine-tune traffic. You can't say, well, if the traffic's going out through R6, then I want it to go this way, or if it's going out through R7, then I want it to go the other way. You don't get to do that. You just basically, you can adjust the metrics, but then that changes everything. Okay, so so basically the issue here is that some of the links are underutilized while others are overutilized. And of course, when you're in the business of selling bandwidth, that's a problem in that you really want to be able to utilize all the parts of your network and really sell all the bandwidth that you potentially have. So Some of the drawbacks of the IGP metrics is that adjusting the IGP metric might destabilize the network, and it could just move the problem on to another part of the network. So yes, we're now utilizing the underutilized part, but maybe we've just now got another part of the network that's kind of underutilized as a result of us changing the metrics. So you end up with some of the links being underutilized and others being congested and overutilized. Some are just maxed out on their bandwidth. So in a nutshell, what we're saying is that the IGP really lacks the control that we want to have in a service provider's network to fine-tune where the traffic goes and to say, well, I want some traffic going here, but other traffic going there, and that particular decision can be made based on where the traffic's actually going to. So we don't get that control with the IGP. Okay, so some of the so we're just looking at basic historically, some of the solutions that have come in to deal with this issue, and it's been an issue for a very long time. Some of the solutions that have come in to deal with the issue, one of them has been ATM, and so what happens is you have these ATM switches, which gives you performance, gives you behavior of the traffic. You set up virtual circuits, you can re-engineer them without physically changing the network, and you can sort of control the traffic flow around the network based on these virtual circuits. So the traffic stats are on a per virtual circuit basis, so you can control the flow of traffic around your virtual circuits. Downside of ATM is that you have to maintain a whole separate infrastructure of ATM switches over the top of your existing routing. There is a certain amount of processing overhead, quite a lot actually, with the ATM system, in that it absorbs some of your bandwidth as well. Scalability, in that it's not something that you can just grow in a nice linear fashion. You have to kind of grow it in chunks. And if you get to the edge of the sort of capacity that you are now, and you need a little bit more, you can't get a little bit more. You've got to go and get a whole other big lot more, which doesn't really make economic sense, and it doesn't integrate that well into your existing network. So you've got your ATM network kind of overlay on top of your IP network. Another solution that was used is frame relay. And with frame relay, again, you use virtual circuits to move traffic to its destination, uses data link connection identifier number to separate the virtual circuits, and it has built-in congestion control. But then again, you've also got to maintain a separate infrastructure over the top to make that work effectively in frame relay. So with MPLS, so MPLS replaces both of those technologies. So everything that could be done with ATM and everything that could be done with frame relay can now be done with MPLS far more efficiently. So some of the benefits of MPLS are improved route lookup time by using labels to forward traffic, increased scalability, additional control over how traffic moves through the network using traffic engineering. So we get this control that we wanted to have. And here in this diagram here, we've got LSPA. LSP stands for Label Switched Path. You'll get used to that term. LSP, Label Switched Path. So what we do is we set up a label switched path for traffic going out the R6 router and another label switched path for traffic heading out for the R7 router, and we get to control the path that each of those traffic flows take. So we really are in control of that process. Okay, a little note here, which may have caught your attention: improve route lookup by using labels to forward traffic. Okay, so we'll get into this, but basically the fundamental principle of MPLS is this, that compared to an IGP, let's just compare it to an IGP. So compared to an IGP, how does an IGP forward traffic? Looks at the destination address on the header and says, okay, let's look at my routing table. Okay, where do I send that traffic? Let's find an interface that I'm going to forward that traffic out. So it does a lookup on its route table and makes a forwarding decision. MPLS doesn't do that at all. It doesn't forward based on the IP address. It forwards based on this thing called a label. So we'll get into that and see how they work. So here's another benefit of MPLS. Service providers can offer different technologies like ATM, frame reload, Ethernet, IPsec over the same infrastructure. So they don't have to go and get something different. So if they've already got a ATM, which many of them have, they can still offer it, but they can integrate it with MPLS inside their core infrastructure. So I will say though that like things ATM and frame relay are definitely, you know, on the way out. So no one's replacing that gear. Okay, it gets to the end of life, that's it, it's gone. It's just that many customers already had these systems in place, so you didn't have to mess with. Basically, the point here is you didn't have to go and mess with your customers and say, hey guys, you've got to change everything. No, you don't have to do that at all. You can keep everything exactly the same and just put MPLS in your core network. Okay, and then over time, when you put new customers on, you might transition them to an MPLS connection directly down onto the customer site. So that's the point there. Okay, so let's get into taking a look at how this actually works. So, as I said before, with an IGP, as you know, the IGP makes a forwarding decision based on the IP address in the packet header. So the packet arrives, it unpacks the frame, takes a look at the IP header, reads the network number, does a route lookup, and then chooses an egress interface and forwards the packet out. Okay, so that's traditional, that's IGP routing. However, with MPLS, we don't route based on the IP address. We route based on a label. So we have our layer 2 header, which is our frame, our MAC address. We have our layer 3 stuff here, which is in the data block. And right in between those two, we pop in this little thing called a label, really, which is an MPLS, called a shim header. So it is a label which is added right after the layer 2. So, which is why MPLS stands for multi-protocol label switching. Okay, so we put this label into the right in the packet there, in between the layer 2 and the layer 3. So the packet is popped in at the beginning of the path. So this is called a push operation here. So the header is prepended to a packet with a push operation at the ingress node. So that's important, at the ingress node. So here we have traffic transiting through the service provider's network, coming in at one router, going out on another. Well, at the ingress where it comes in, we pop this label onto the packet. Okay, I shouldn't use pop, because actually pop is the term that is used for taking the label off. If we push, we push this label onto the packet, okay, with a push operation. So the label goes into the packet, and then the forwarding decision through the network is based on the information in the label. And then when we get to the end of our label switch path, what we do is you take the little label off the packet, and that's called pop operation. So the push is putting the label on, the pop is taking the label off, and that is normally done at the penultimate router. And the penultimate router means the second last router. So, which is actually the meaning of the word penultimate. So that means not the last router, but the one right before the last router on the path. So what happens is the second last router gets this packet with a label. It will do a lookup as to where do I need to send this to, and then when it sends it, it'll pop the label out and send it without the label. Okay, so it will arrive at the very last router in the path without its label. So it will transition through the path based on the information in the label. Okay, so let's take a look at that idea. So here's the label. So the purpose of the label is to associate that packet with a label switch path. Okay, so we're going to forward traffic through our network, not based on the IP address, but based on the value in this label. And this is the 20 bits here. This is actually an ID in there, a value, a number. We also have a class of service marking in there as well. There's this other little bit here as well, this S bit. And really, the point of that is that you can actually have multiple levels of labels. So you can have more than one label. You can have an inner label and an outer label. And this little field here is to identify whether this is the inner label or the outer label, because you can actually have paths within paths, label switch paths within label switch paths, in actual fact. And then the time to live, TTL. Okay, so there's our 32-bit header. It's actually a very small header, so very small. And the other thing about it is it's very, very fast to read it as well. So this is a very fast operation. The frame arrives at the router. It doesn't even have to unpack the header of the layer 3 header and read the IP address at all. It doesn't do any of that. It just reads the value that's in the label, which is a very quick operation. That value enables it to make a forwarding decision, and it will then forward the packet on based on that label value. Okay, so so we've got a label value. We've got this class of service here. Now with that class of service, it does allow us to do all the things that we might normally do with class of service, and that we can prioritize certain traffic over other traffic. But on top of that, we can actually prioritize, as we go on, we'll discover we can prioritize certain label switch paths over other label switch paths as well. So we do get a lot of control. This is the thing about MPLS. It gives us so much control over the traffic on our networks. And because here's the thing about a telecommunications company that you really need to keep in mind, is that within a telecommunications company, within its business model, it is never economically viable to build a telecommunications network that can carry all the bandwidth and all the traffic that all the users may want to send or receive all the time. It just doesn't make economic sense to do that. So what that means is there will be times of congestion, okay? And when there's times of congestion, we want to be able to control what happens. We want to be able to service the customers that have paid for a premium service and make sure that they get, what they're paying for. So we're talking, just a little discussion before we got started here about just in our local Gold Coast region here, just giving you an example of how MPLS is used, in that one of our local service providers here provides the connectivity between all the different sites of the Gold Coast City Council. And so with that, when the Gold Coast City Council outsources that connectivity or that service to that provider, it comes with a service level agreement that says this is the level of service that you must provide. So to get paid that particular check every month, you need to provide us with this level of service. And when there's times of congestion, we still have to make sure that that level of service is provided to those customers that have those arrangements. Excuse me. So we do get to we even though we've got this class of service in there, we still get to even prioritize certain paths over other paths. You can have higher priority paths. Okay. So basic principle is that we insert a label into the packet, and we're then able to make forwarding decisions based on the label rather than the IP address. So labels can be assigned manually or by a signaling protocol. Here we go. So we'll do in the labs. You'll actually do both of these. You'll set up what's called a static label switch paths, and then we'll get into configuring these things called signaling protocols, which you basically put some information into the signaling protocol and you say, well, I want a path from here to there, give us some other parameters, and it'll build the path for you through your network. It'll find a path that meets your particular requirements. And you get a lot of control over this. You can say, well, I want a path that starts at this ingress router, goes to this egress router, but I want it to go through this router in the middle. I want it to go through R4. And my path has to go through R4. You can say all kinds of things. So you get a lot of control over your path. You can decide how much bandwidth it needs to have, where it needs to go. So there's you do labs and all this, but you get a lot of control over exactly where this path goes through the network. Okay, so labels can be assigned manually or by a signaling protocol. And as I said, the signaling protocol kind of automates the path creation process. It's very, very cool the way that works. And you can do this in every LSR. LSR, bit of jargon there, label switched router. Okay, so in other words, every router that is participating in the MPLS protocol is a label switch router. And I'm not saying you need to have a special router. You go out and order from Juniper a label switch router. There are routers which have MPLS capabilities sort of built into them. And of course, when they're in a label switch path, they are a label switch router. Label values will change at each segment in the path. What do I mean by that? Well, what that means is that you put a value into the label. The packet arrives at the router looks at the value and looks in its lookup table and says, okay, I need to forward that out this interface. What that router actually does is a thing called a swap operation, where it puts that old label out, puts a new label in, and then forwards it on to the next router, and the next router will be able to make a forwarding decision based on the new label. We'll get into this in a bit of detail. So this is the swap. So the label switch router is going to do a swap operation, incoming label swapped with a different outgoing label. So the point of that is the labels only have local significance, meaning that the forwarding decision that is made is based on a label value that router is expecting to receive from its downstream router. So that router, that packet that arrives comes in from the downstream router. the value, the router is expecting that value on that label. It has a lookup table which tells it what to do with that particular label value. It will then do the forwarding operation and also swap the label with a new outgoing label that its upstream router will be expecting. So they only have local significance. Now there's a few reserved values that mean specific things. 0 is what's called an explicit null. 1 is a router alert label. 2 is IPv6 explicit null for 2, and 3 is an implicit null. And 4 and 15 not used for anything at all. We will actually use in our paths, we'll use 0s and we'll use 3s to do particular things, to perform particular functions, because they actually instruct the receiving router to perform a particular operations when they see those values in those label values. So this is an example. So here's an example. Say, well, what label values do I have? Here's an example of a label value right on this next slide. So it is a 1, 0, 0, 0, 0, 5, 0. Here we have the label value. Okay, so we have this label information base, which is really the lookup table. So this is really my route lookup here for labels. On the Juniper router, the table name is mpls.0. So it's automatically created with label values for 0, 1, and 2 when you configure the protocol. Tables used by transit routers to make forwarding decisions. MPLS.0 table maps the incoming labels with the outgoing label and next hop for the packets. So here we have, this is a table here. We go down and take a look at some information in here. We have got an incoming value of 1000050. The lookup here, you've got an IP address that it's going to via GE1006. So there it is there, 1006.0. So that's our outgoing interface. So that's the forwarding information right there. So basically what we're saying is forward this packet out of GE1006.0, and also there's a swap instruction in there which says swap 100515. So what will happen is when this router receives this packet with a label value of 100050, it will do two things. It will swap that label for a new label of 10000515 and forward the packet out of interface GE1006.0. And it will know to do that because of the information that is in this MPLS.0 table. Okay, so that is basically its lookup, its label forwarding lookup table, MPLS.0. So when MPLS is configured on a router, this new table is created. Okay, this new table is created. So what we're doing then is we're able to forward packets. This is kind of important. We're able to forward packets completely independent of the IP addresses that are in the header. So we don't care what the IP address is. It doesn't matter, because we're making forwarding decisions not based on the IP address, but based on the label value, which means that we can control the flow of traffic around the network regardless or irrelevant. The IP address at that point becomes irrelevant in some respects as to the forwarding decisions that are made within the internal service provider network and where the label switch paths can go. So we're not constrained by our usual IGP forwarding mechanisms. We have a totally separate forwarding mechanism, which is built into the MPLS system. Okay, that gives us all kinds of flexibility as to how we can control the flow of traffic around our networks. Okay, so just recapping there, we have this table which is automatically created when we configure MPLS. It's used by transit routers to make forwarding decisions. What's a transit router? That's any router that is in a label switch path. So a router that is not the ingress router, is not the egress router, it's a router somewhere in between. Okay, that's a transit router. The MPLS table maps the incoming packets with outgoing label and a next hop to forward the packets. So the swap information is in the MPLS.0 table. So it will be sent out with a new label. Okay, let's get into a little bit of this terminology that we've been throwing about here. We have label switch routers. So an LSR is a label switch router. So it does MPLS packet forwarding and it can do label switch path setup. What kinds of routers can do that within the Juniper series of routers? Well, we have M series routers, T series routers, and MX series routers can do that. In our labs, we're using the MX series router. All these routers support the label switch router capabilities. In this course, we don't call them label switch routers, just call them routers because, well, they're all label switch routers if they're handling MPLS. So we just call them routers. Okay, so there we are. There's our label switch routers. LSP. An LSP is a label switch path. So here's an example of a path. This path starts at R2 and ends at R6 in this case. So there we are. That's the label switch path. Really important point about a label switch path is that it's unidirectional. Okay, unidirectional. It goes one way. As you know, traffic in a network is always two-way. Okay, so for two-way traffic, we need two label switch paths, don't we? We need one in one direction and one in the other direction. And you get to control exactly the path that each of them take. Okay, a bit more terminology. Ingress router. The packet enters the label switch path at the ingress router, sometimes called the head-end router. In this case, this diagram, that is R2. That's our ingress router. It is upstream from the other routers, performs a label push operation. So there it is, it's pushing the label onto the path, onto the packet, sorry. And that then sends that packet along that label switch path. So it's the ingress that performs the push. Transit routers, we don't need transit routers. We can have just an ingress and an egress router in the path. So you can just have two routers in a path. But if we have routers in the middle, they are transit routers. They perform the swap operation. So, and they also forward the traffic to the next hop in the label switch path. So we have a label swap happening on the transit router. The transit router, as you saw previously, has this MPLS.0 table, does a lookup. In that table, it will tell it what the forwarding interface is, what the lookup will give it forwarding information for the egress interface, and also the label value for the swap is also in that table. Then we have the penultimate router, which is the second last router. In this case, in our diagram, it's router 5. it normally pops the label stack. So it will pop the label and not do a swap. So it will then be forwarded onto R6 without a label. And then that's because R6 is the end of the path. R6 doesn't need to do an MPLS lookup, so it doesn't need a label. So it will make its forwarding decision based on its routing protocols, which maybe it's IGP or maybe it will use BGP to make a forwarding decision, being that it's part of a service provider network, and being that it could be on the edge of the network, it may be forwarding based on BGP to its destination. Okay, so there we are. We had a look at the functions of the different routers there. Last one, the egress router, which is the last router in the path, called the tail end router, downstream from other routers, forwards packets based on the IP address, not the label. Okay, so basic concepts. Okay, we've had a look at the fact that we are forwarding packets based on this label value rather than an IP address, that we have this ingress router which does a push operation, we have our transit routers which do swap operations, and we have our penultimate router which does a pop operation, and our egress router which simply forwards the packet based on its IP address. Okay, let's look at some configuration for MPLS. So let's look at interface configuration. Default behavior of an interface is to accept only IP packets, so protocol family INET. So to have that packet accept MPLS packets, we have to configure the protocol family MPLS onto the interface. This is the example of that down here. We add the family MPLS configuration onto an interface. So we've still got INET. Okay, we're just adding MPLS. Protocol configuration under the protocols hierarchy, you specify the interfaces that are running MPLS. So we've done two things. We've gone to the interface itself and included family MPLS. Then we've gone under the protocols MPLS hierarchy and included the interface name down there. So what you can do, if pretty much everything's running MPLS, you can simply put interface all and then exclude your management interface, which is of course on these MX series routers, they all have this FXP0 interface, and that interface is not or will not pass transit traffic. So its only function, its only purpose is for the administrator to log into the router and manage it. That's all it's there for. Okay, it's to provide administrator access to the router management. So it's the management interface, and of course you're not going to be passing MPLS on that interface. So you could just go and disable that interface. You're not disabling the interface. All you're doing is disabling MPLS on the interface under the edit protocols MPLS hierarchy there. Okay, so that's a pretty good way of doing it. You can enable all the interfaces except your management interface. Okay, so configuring the ingress router for a static label switch path. Now you will do a lab on this. I will say that in an operational environment, you probably won't ever configure a static label switch path, but for the purposes of learning the concept of MPLS, it is very useful to go and configure a static label switch path just so you understand what's happening along the path. Okay, so in an operational network, you will always use what's referred to as a signaling protocol to create a label switch path for you. And you will configure the signaling protocol. But for the purposes of us learning how these things work, we are going to go and set up a static label switch path. So Under the Edit Protocols MPLS hierarchy, we will use the term static label switch path and then give it a name. So that's a user configurable name. Then we set up the ingress. So we're going to tell this path what is your starting point. So in actual fact, the starting point is the router on which we are configuring this particular label switch path. So the label switch path, here's an important point. The details about the label switch path are always configured on the ingress router. So the ingress router really sets up the label switch path. So we have the name, ingress, and we have the next hop, so address or interface of the next hop router. The address of the egress router. So this is where we set up the end of the path as well. So we're going to tell, so this is we're doing all this on the ingress router. So we're setting up the next hop. What is the last router? So what is the end of the path? Where are we heading? Where's this path end? We know it starts here. Where does it end? And what is the label that we're putting on this path, so or on this packet? Sorry, what's the push? What's the value, the label value that we're pushing onto the packets that are going into this path? So every packet that goes into that router will get, and that will belong to this path, this name, will get this value, the same value. Okay, the same value. So all the packets that are headed down this particular path that we are creating will get this label value pushed onto them by this router. Okay, and really what that means is that this value really signifies the fact that these packets belong to this particular path, because they're going to get that same value pushed onto them. Okay, and all this is happening on the ingress router. So it's the ingress router that really sets up the path. The ingress router will set up the name of the path. The next hop along the path also sets up the egress router and also sets up the first label value. Okay, on a transit router, this is for our label switch path. On a transit router, under Edit Protocols MPLS, we're still going to use the static label switch path command, and of course the name that we put here will be the same name that we put onto the ingress router. So we're referencing the same label switch path. Transit incoming label value, what do you think that's going to be? Well, it will be exactly the same value that we put here on the push, okay, of our ingress. All right, so that value, whatever value we put here as our push on our ingress, that will be the value that we put here on our next router along as the incoming label value. Next hop address or interface of the next hop router, and then the outgoing label for the swap operation. So all the transit routers look like that. Okay, so the name should be unique, so we don't use the name twice. So every label switch path has a unique name. Label values. Static label values will be from 1 million through to 1 million, well, that number. You can also send the label 0 to tell the next router to pop the label. So we still get to use this reserve value which actually instructs the router that receives a label value of 0. So when a router receives a label value of 0, that tells that router to pop the label and not swap it. Okay, so it really is a pop command. Okay, so what have we discovered so far? The fact that the ingress router, let's go back and look at the ingress router here. We've discovered that we set up the label switch path on the ingress router. We put the name, we put the next hop address, and we also put the egress router is defined. So the actual IP address of the ingress router, of the egress router is defined when we set up the path, and the value is set up. Transit routers, we have an incoming value, next hop, and an outgoing value for the swap. Unique name. Okay, so how does traffic know that it's going to be going into a label switch path? Well, the routes that are associated with a label switch path are installed into the INET3 routing table. And what we're actually going to do here is we're actually going to use the BGP protocol to direct traffic into a label switch path. So why would we be using BGP to do that? How come, what's the BGP protocol suddenly doing here? Actually, in fact, we're going to be doing a lot with BGP in this MPLS topic. Why is that? Well, because we're working in the service provider environment, and the service provider environment utilizes BGP for all of the routing between that service provider and anywhere else. Okay, anything that's going outside of that autonomous system, that routing is going to be handled by BGP. So we really are using BGP to handle the routes that are going between, between our autonomous system and others, but also when the BGP route, when BGP forwards the traffic into our environment, it is actually going to be hitting a router that is configured with BGP, and it's actually the BGP protocol then that's going to have to direct the traffic into the label switch path. Okay, so that's going to be one of the jobs of BGP. So BGP will install a label switch path as the next hop for transit destinations. So internal destinations are not associated with a BGP next hop and therefore do not use, excuse me, an LSP by default. So the point here is that MPLS and therefore label switch paths are used for transit traffic that's coming in on one router of the service provider and exiting, going right through the service provider and going out on another router. So none of this traffic is destined for any device or any node or any IP address that is within that service provider. Okay, it's going somewhere else. Okay, coming in, going out. So that is the primary purpose of MPLS and label switch paths. Transit traffic comes in on one, goes out on another, and what we're trying to do is to control the path that it takes on the way through. Okay, that's our goal. So, so BGP won't have any internal destinations because it's always interested in traffic that's going into another autonomous system. So it won't be using label switch paths. Okay, so this next little lesson here is we're actually going to delve for a moment. We're going to delve into BGP for a minute here, and just sort of get into how BGP works. We're going to get into some of the limitations that BGP has with how it forwards traffic and how it, more like how it advertises routes, and we're going to get into some of the limitations and some of the issues that are arise and how to resolve those issues, how to solve those problems. Okay, so we're going to kind of dive in for a minute here into BGP. Might have to do a bit of a refresher here on some of the things that BGP does and doesn't do, and how it works. So what we'll do is we will in fact get into that after our lunch break, because we'll spend a little bit of time thinking about this. So we'll go to lunch, and when we come back at 1, we'll delve into this BGP issue here and get our heads around that. So we'll catch you back at 1 o'clock.